So now we're going to take a look at our decomposition reactions, starting with aluminum carbonate. So aluminum carbonate. We have the same three steps that we need to do, and that is write your symbols and your combos. So that's one step. Step 2 is formulas. Step 3, balance. All right, so aluminum carbonate yields. Now, if you look over at the right side of the screen, I tried to get it so it could show up and I wouldn't have to flip back and forth. So there's a little thing right here that says metallic carbonates. See metallic carbonates? And they turn into metallic oxides and carbon dioxide. Since the metal here is aluminum, the metallic oxide is going to be aluminum with oxygen, and carbon dioxide is the other product. So now we've done symbols combos. Formulas, aluminum is +3, carbonate's -2, so we had to put a 2 down here. There we go. Nope. Someday I need to really learn how to use this thing. All right, there we go. And then carbonate over here. So since that's a -2, you had to have 3 of those and 2 of those. All right, now the aluminum is +3, again, on this side, -2, so you have to have a 2 and you have to have a 3. And carbon dioxide is just as it stands, CO2, carbon dioxide. Step 2 is complete, formulas. Step 3, balance. Well, look over here, you got 2 aluminums, you have 2 aluminums, so that's fine. Carbons, in this parenthesis, there's 1 carbon, but there is a 3 outside of the parenthesis, which means that there are 3 carbons total on the left side of the arrow. So on this side of the arrow, you need to put a 3 in front of the CO2. All right, I had to go back and fix that because my pen erased it for me. All right, so now I've got a 3 in front of the CO2, which gave me 3 C's. That in turn multiplied the oxygen on this side by 3, so there are 6 oxygens here. I'll write it up just up here. This is not part of the equation, but just put a 6 up there. Plus these 3 make 9 total oxygens. So you got 3 plus 6 makes 9 on the right side of the equation. On the left side of the equation, there are 3 inside the parentheses, but there is a 3 outside of the parentheses, so you end up with 3 times 3, which makes 9 oxygens on the left side, so that was finished. You recognize a decomposition reaction by the fact that there's only 1 reactant, and it's going to turn into something else. So let's take a look at the next one. These are all decompositions. So I've got an iron, 3 chlorate. Chlorate is a polyatomic ion again. Iron is +3 and chlorate's -1. We'll just go ahead and put the charges up here. And that yields iron 3 chloride. And we know that because down here it tells us that metallic chlorates decompose into metallic chlorides and oxygen. So the metallic chloride would be iron with chlorine plus oxygen. So we'll put a little plus sign in here, and then oxygen. Now remember, oxygen is part of Brinkelhoff, so it has to be O2. Now we have our symbols combos down. This is +3, this is -1, so to write the formula correctly, we put parentheses around that and put a 3 outside. We're going to assume on all these reactions that the charges don't change for most things. So it's +3 and that's -1, so we would say I have to have a 3 down there. And the oxygen is as it stands. Inside the parentheses over here, there's 1 chlorine, but there's a 3 outside, so that makes 3 chlorines total. I have 3 chlorines, so that's good. However, here's a problem. I've got 3 oxygens inside the parentheses. There's a 3 outside that gives me 9. So on this side I only have 2. So this one's kind of a weird one. You have to have a common multiple of 9 and 2, which is 18. So if I put a 9 in front of 2, that gives me 18. if I put a 2 in front of that, it gives me 18 oxygens, because 3 times 3 is 9, times 2 is 18. The side effect of that was it gave me 2 iron atoms, so I had to put a 2 over here, and that multiplies the chlorine by 6. Oh, but wait, I had 3 on this side, because there's 1 chlorine inside the parentheses, there's a 3 outside the parentheses, which gives me 3 chlorines, times 2 is 6. So the equation is not balanced. All right, the next example of decomposition is a metallic hydroxide. If you look over here, metallic hydroxide right there, it makes a metallic oxide in water. So our metallic hydroxide is KOH, and hydroxide is a polyatomic ion. You find it at the bottom of the page. That is one of the couple of or 3 polyatomic ions that end in IDE. That when I say bottom of the page, I'm talking about the bottom of the periodic table. All right, and then the potassium oxide would be our metallic oxide plus water. Now our symbols are finished. Formulas, that's +1, that's -1, so that's good. +1, -2, oh, that's not good, so I have to put a 2 down here. Water's water, so that gave me 2 Ks, so over here I had to put 2 K, that gave me 2 H's, I have 2 H's, 2 O's, an O here and an O here make 2 O's, so we're good. All right, now the acid. The acid's a little bit more tricky for decomposition. So phosphoric acid, you have to recognize first of all that ic becomes 8. So remember, for polyatomic ions in acids, ternary acids, the ATE becomes IC ending. So phosphoric means that you've got phosphate. And you have an H in front because it's an acid. So it's going to turn into a nonmetal oxide. If you look over here, acids make nonmetal oxides plus water. So a nonmetal oxide in this case would be P with O and water. All right, so I'll go back and do the formulas. The hydrogen is +1. So we're going to put a 3 down here because phosphate is -3. And on this side, this is the most confusing part of these decompositions. So we're going to assume that the oxidation states of all these stay the same on both sides. So let's take a quick look at the phosphate ion. Do it down here. The charge on phosphate is -3. In a polyatomic ion, the sum of the oxidation states needs to equal the charge on the ion. We know that oxygen is -2. And there are 4 oxygens in this ion, so we get a -8 total oxygen charge. So -8 plus something has to equal -3. What is X? It's 5. So the phosphorus is +5 up here. And oxygen's -2. So 2 times 4 is 8. 8 plus 5 is that -3. So over here, phosphorus is +5. We'll assume it stays the same. That's -2. So we'd have a P2O5 for our formula. And these are, once again, probably you have to think more on these than the others. And we are probably oversimplifying a little bit in that we are assuming that they all continue to maintain their same charge from side to side. All right, so now if you have 2 P's, we're going to put a 2 over here. That gave us 6 H's, so you put a 3 over here. 5 plus 3, because now you have 3 oxygens. There's 1 oxygen times 3 is 3, so 3 times plus 5 is 8, and 2 times 4 is 8, so we're finished. Last example of decomposition, HgO, mercury 2 oxide. Now this is just a straight binary decomposition. So it says over here, binary compounds make the individual elements. So we would have mercury and oxygen. What do we know about oxygen though? It's part of Brinkelhoff. So when it's by itself, it has to be in pairs. All right, so now you got 2 O's, you got 1 O, so you're going to put a 2 there. That gives me 2 Hg's, gives me 2. So I've done my 3 steps, and I'm finished with symbols, formulas, balance. That's it for decompositions, and I'll come back with another video on synthesis.